Good morning, chemistry students. This is Mrs. Krumschreiter, and this is your final day of Chapter 7 notes. Today you're going to learn how to calculate empirical and molecular formulas. Again, you're going to want to have your chemistry toolkit handy, you're going to want to have your periodic table handy, and you're going to want to have a calculator handy. So, we talked about how to calculate the percent composition and how to use percent composition as a conversion factor. Today, we're focusing on empirical and molecular formulas. So, eventually, you're going to calculate empirical formulas here. So, keep in mind that the formulas for some compounds show the most basic ratio of elements. Right, specifically, formulas for ionic compounds do this because remember, when we're writing the formulas for ionic compounds, we write our symbols, we write our charges, we crisscross, and we make sure it's the lowest whole number ratio. Because we make sure it's the lowest whole number ratio, that means that that formula is just showing us the most basic ratio of elements in the compounds. Okay? However, remember with molecular compounds, our prefixes became our subscripts, and we did not reduce them. Okay, so in molecular compounds, sometimes we don't have the most basic ratio or simplest ratio of elements. Multiplying that ratio, that basic ratio, by any factor can produce formulas for other compounds. So our definition of an empirical formula is that an empirical formula gives the lowest whole number ratio of the atoms or moles of the atoms in a compound. So to kind of explain what we mean here, for example, when we look at the formula H2O, right, you're already pretty comfortable with the fact that you can interpret this as 2 hydrogen atoms and 1 oxygen atom. But the other way that you can interpret this is that you have 2 moles of hydrogen atoms combining with 1 mole of oxygen atoms. Okay, so that's kind of this second part here where we're talking about or the moles of the atoms in a compound. So our empirical formula may or may not be the same as the molecular formula. So, for ionic compounds, again, because that last step is simplest whole number ratio, empirical formulas and formula units for ionic compounds will be the same. But when we're talking about molecular compounds, and our prefixes become our subscripts. Sometimes our empirical formula is the same as our molecular formula, and sometimes it's not. An example of it being the same is water, right? 2 to 1, that's the lowest whole number ratio of hydrogen to oxygen in water. So H2O is both the molecular formula for water, but it's also the empirical formula for water. For example, okay, hydrogen peroxide okay. The formula for hydrogen peroxide is H2O2. That's our molecular formula. Now, is 2 to 2 the lowest whole number ratio? No. Okay. So our empirical formula for peroxide is HO. So peroxide, hydrogen peroxide, is an example where our empirical and molecular formulas are different from one another. Water is an example where our empirical and molecular formulas are the same. Again, remember our definition of molecular formula that we learned a while ago is that a molecular formula tells the actual number of each kind of atom present in a molecule of compound, specifically of a molecular compound. So you're going to see, because we're going to do this here in just a few moments, that the percent composition of a compound can be used to calculate the empirical formula of that compound. So basically what I'm saying here is if you have are given the percent composition of an element of a compound, you can figure out the empirical formula of that compound. So, how do we actually calculate that? Well, kind of the steps that we're going to go through is we're going to use our percent composition to get a ratio of masses. We're going to use that ratio of masses to get a ratio of moles. And then we're going to use that ratio of moles to get our lowest whole number ratio. So, our example, a compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. We want to know what is the empirical formula of the compound. Now, on your outline, you probably have enough room to kind of take your page and kind of split what you have into 1/4 and 3/4. I don't have that kind of room on my iPad, okay? So on kind of your 1/4 part, we're going to list the steps that we solve, okay, to solve these problems. And then I'm actually going to show you working that problem here. Oops. Sorry about that. Did it again. Okay. But you should be able to split your page so that you have the steps, and you probably just need like 1/4 of your page for that, and then 3/4 of your page for doing the actual problem. Okay, so we're going to kind of explain the steps, and then actually we'll do it this way. We're going to explain the steps, and then we're going to do the problem. Okay, so step number 1 when we're doing this problem, okay, any of these empirical formula problems, is we're going to assume we have 100 grams of our compound, because therefore our percentage becomes a mass. Okay, so because we've been given percent composition, we're going to assume we have 100 grams of our compound. That way, our percentages that are here are just going to become grams, because percent means per 100. So, based on that, we're going to assume then that we have 25.9 grams of nitrogen and 74.1 grams of oxygen. And you want to set this up with space for conversion factors, okay, and going down your paper, just like I just did. Okay, so if you split your paper into the 1/4, 3/4, this should go in the 3/4 section as close to the edge of your 1/4 part as possible. Okay, so that's step number 1, which we just did. Step number 2, okay, we're going to use our molar mass conversion factor to change or convert mass to moles. Because remember, our definition back here of empirical formula was it was a lowest whole number ratio of moles of atoms. So we need to take what we have as mass data right now and convert it to moles. So we're going to use our molar mass conversion factor. Remember, we need units to cross out, so grams of nitrogen will be on the bottom, moles of nitrogen are going to be on the top. Grams of oxygen will be on the bottom, moles of oxygen will be on the top. The easy numbers for these are moles, right, because that's 1. Our gram number, that comes from our periodic table. We want to make sure we use at least 3 significant figures. So for nitrogen, I'm going to go ahead and use, okay, 14.007. And for oxygen, I'm going to use 15.999. Remember, those numbers just came from our periodic table. Okay, and we're going to do that math. So again, I'm going to put in my calculator 25.9 divided by 14.007. And I'm going to go ahead and write my answer with 3 significant figures. So I end up with 1.85 moles of nitrogen. And I'm going to store that in my calculator as A, just because I'm probably going to need that number at some point. And I just kind of keep track of the fact that I've done that. 74.1 divided by 15.999. And with 3 significant figures, I get 4.63 moles of oxygen, which I'm going to go ahead and store in B. Now, remember, I'm trying to write a formula here. And right now, my formula would look like this. N 1.85, O 4.63. Can I write a formula like that? No, right? I can't do that. I have to have whole numbers. So that means I'm not done yet. Okay? And so I'm going to have a third step. Okay? So my third step is that, okay, we must have whole numbers, as we just talked about. So the trick to getting whole numbers is we're going to divide all the numbers by the smallest value. And at that point, with the problems I'm going to give you, after you do that, you should have whole numbers or wholes and halves. If you don't, then you should check your math. Okay, so this is after, right? This in parentheses is after you do this calculation. You should either have whole numbers or wholes and halves. So now we're going to go ahead and do this, right? So our smaller number is our nitrogen. So we're going to take both of these and divide them by the 1.85. Right? That makes this 1.00 moles of nitrogen. And again, I'm being consistent about my significant figures. So I'm going to take my B and divide it by my A. And with three significant figures, I get 2.50 moles of oxygen. Now, again, remember, we said we should either have whole numbers or wholes and halves. So we have a whole number and then we have a half. So this is okay. What this means right now is if I take 2.5 and make it an improper fraction, it'd be 4 5/2, correct? So what this means is right now my formula is N1, O 5/2, but I can't have a half. So how can I get rid of that half? I'm going to multiply through by 2. Okay, so kind of back over here. Step number 4. If we have halves, we're going to multiply all the numbers by 2 to get whole numbers. Okay, so what I just said is either at the end of that previous step, we either should have had whole numbers or wholes and halves. Because we have half numbers here, we have to get rid of that half. And our way to get rid of that half is to multiply this by 2. I realize this looks like it might be squared. Oops, never used that before. Okay. So what we want to do is we're going to take this and multiply it by 2. So N is going to become 1 times 2, which would be 2. O, 5/2 times 2 becomes 5. That is our empirical formula. So this is our answer to our problem. So again, those steps. We assume we have 100 grams of compound, therefore our percentage becomes a mass. Because we have mass, now we're going to use our molar mass as a conversion factor to convert mass to moles. At that point, we either should have whole numbers, okay, and if we don't, then the trick is we're going to take all of our whole numbers and divide all of our numbers by whatever the smallest value is. And after we do that, we should either have whole numbers or wholes and halves. If we don't have wholes or wholes and halves, then we should check our math. If you do have halves, then you have to multiply all your numbers by 2 to get whole numbers. So those are those steps that we just did to do this problem. So that's how you calculate an empirical formula, is using those steps that we just wrote. So now that you can calculate an empirical formula, which is that lowest whole number ratio, how do we use that to calculate molecular formulas? So again, we're going to start with this idea that the molecular formula of a compound is either the same, as its experimentally determined empirical formula, or it's a simple whole number multiple of its empirical formula. So to kind of give you an example of this, I'm going to have a formula. I want you to calculate the molar mass. I'm going to spread this out just a little bit more. Remember, you don't have to show work for molar mass, but this is going to be in grams per mole. And then I want you to identify this formula as to type. So is it an empirical formula where it's the lowest whole number ratio, or is it a molecular formula? Okay. And 1, 2, 3, there's going to be 6 of these. 2, 3, 4, 5, 6. Perfect. I have 6 slides. All right, so our first formula, CH. Maybe I'll do these in different colors. Ooh, yeah. Feeling colorful anyway. So our first one, CH. Okay, our second one, C2H2, which is ethine. Next one, C6H6, which is benzene. You don't have to know the names, I'm just giving them to you. CH2O, which is methanol. C2H4O2, which is ethonic acid. And C6H12O6, which is glucose. So go ahead for these and calculate the molar mass and decide whether they are empirical formulas or molecular formulas. And if you need more time, okay, then when I give you, pause the video. So for these, carbon is 12, hydrogen is 1. So 1 carbon at 12 plus 1 hydrogen at 1 makes my molar mass here 13. Oops, I was going to use colors. Okay, 13. And this would be an empirical formula because 1 to 1 is the lowest whole number ratio. For ethine, 2 times 12 plus 2 makes a molar mass of 26 grams per mole. And this is a molecular formula because 2 to 2 is not the lowest whole number ratio. Next we have, well, let me give you a little preview, something to notice. For ethyne, my one in red, my formula in red, if I wanted to write the lowest whole number ratio, the empirical formula, it would be CH, right? And what would I have to do to CH to make it C2H2? I'd multiply it by 2. Notice I also would take the molar mass of CH and multiply it by 2 to get 26. All right, let's look at benzene. 6 carbons at 12 apiece plus 6 hydrogens at 1 apiece gives us a molar mass of 78. Again, its empirical formula would be the CH. And if I take 13 and multiply it by 6, I get 78. Right? And what would I have to do to CH to get C6H6? I'd multiply it by 6. This again is a molecular formula. For methanol, carbons 12, hydrogens 1 apiece, oxygen we'll use 16, so we get a molar mass of 30 here. And this is, again, an empirical formula because 1 to 2 to 1 is my lowest whole number ratio. Next, ethonic acid. 2 carbons plus 4 hydrogens plus 2 oxygens gives you a molar mass of 60. Again, my empirical formula would be CH2O, and I would multiply it by 2, and lo and behold, my molar mass of my empirical formula multiplied by 2 gives me my molecular formula. Lastly, glucose, 6 carbons plus 12 hydrogens plus 6 oxygens is going to give you a mass of about 180 grams per mole. Again, its empirical formula is still CH2O, but I would have to multiply it by 6. 30 times 6 gives me 180, and this is a molecular formula. Okay. So notice that there's a relationship between the molar mass of my compound and the molar mass of my empirical formula and how many times I have to multiply. So once you have determined the empirical formula, you can determine the molecular formula if you know the compound's molar mass. Part of what you're going to have to do is you will have to calculate the empirical formula mass of the compound from the empirical formula. So basically all I'm saying is you're going to figure out the molar mass of your empirical formula. So you're going to take your formula just like we just did right here, and we calculated all these molar masses, okay, in this column here. You would do that. So basically this is the molar mass of your empirical formula. That's what your empirical formula mass is. You're going to divide the molar mass by the empirical formula mass to get the number of empirical formula units in a molecule of the compound. And this is the multiplier to convert your empirical formula to your molecular formula. So to find out what I have to basically kind of another way to write this, okay. I know that my empirical formula times some multiple will give me my molecular formula. That's what we saw here, right? This empirical formula here times this multiple of 2, this empirical formula here times this multiple of 2 gives me this molecular formula. Okay? To figure out what that multiple is, I'm going to take the molar mass of my compound, or of my molecule, and divide it by the empirical formula mass. So, let's do a problem and take a look at how we actually do this. So this problem, I want you to calculate, or we're going to calculate, the molecular formula of a compound whose molar mass is 60 grams per mole, and empirical formula is CH4N. So my empirical formula is given. That's the CH4N. I don't know what my molecular formula is. That's what I'm trying to figure out. But I know that the molar mass of this molecular formula is 60 grams per mole. So I know I'm going to take CH4N, multiply it by some multiple to get my molecular formula. To find that multiple, I'm going to use that equation. So I need the molar mass of my compound divided by the empirical formula mass. Well, I have my empirical formula, so I can figure out my empirical formula mass. I'm going to add together 1 carbon plus 4 hydrogens plus 1 nitrogen, using my atomic masses from my periodic table. So carbon is 12.011. There's 4 hydrogens at 1.0079. And there's 1 nitrogen at 14.007. So that gives me 30.0 grams per mole as my empirical formula mass. So how do I find my multiple? My molar mass, which was given in the problem, is 60, divided by the empirical formula mass that I just calculated, which is 2. So that means I'm going to take CH4N and multiply it by 2. So my answer is, for my molecular formula, is C2H8N2. That is the molecular formula Now, one way that your textbook sometimes makes these problems a little harder is that instead of giving you the empirical formula like this problem did, they'll make you do a problem like this first, where they give you percent composition and you have to calculate the empirical formula. So that brings us to your homework, which is on page 195, 39 through 43. Make sure you're showing all your work, like the problems that we've done in our notes. Have a great day. I'll talk to you tomorrow.